let's chat about the change of coordinate matrix. Okay, so remember that if alpha and beta are two ordered bases of a finite dimensional vector space V, then Q, the matrix representation of the identity transformation from alpha coordinates to beta coordinates, is called the change of coordinate matrix. And we say Q changes alpha coordinates into beta coordinates. Now there's going to be a lot of discussion about a particular kind of linear transformation called a linear operator. That's a linear transformation from V to itself. So here's the main theorem of this video. Let alpha and beta be two ordered bases for a finite dimensional vector space V, and let T be a linear operator. If Q is the change of coordinate matrix from alpha coordinates into beta coordinates, nice to have it listed there, right? Then T alpha equals Q inverse T beta Q. So that might be a lot to process, but really what it's saying is if you know the matrix representation of a linear transformation in one ordered basis, you can get to the matrix representation in another ordered basis as long as you have the change of coordinate matrix. So for this theorem, what we need to do is we just need to remember that T is equal to the identity map on V composed with T is equal to T composed with the identity map on V. So that's pretty obvious, and you might say, why on earth is that relevant? Well, because if you want something like this, let's just think about what it would look like to have Q on the other side. So if you multiply on the left by Q alpha, you're basically looking at something that would look like this. Q times the matrix representation of T in terms of alpha. Well, that equals, remember the definition of this thing, IV from alpha to beta, T alpha, right? Well, the composition, remember we showed that the composition of two matrix representation of linear transformations is the matrix representation of the composition of the linear transformations, right? Well, but that map, remember, is exactly the map T IV, right? So these are exactly the same linear transformation, which means their matrix representations are identical. Now we break it apart just the way we put it together there. Notice IV is going from alpha to beta. T is in beta coordinates here, right? This feeds out beta coordinates. This has to handle beta coordinates. But what is this? This is T beta Q. Multiplying on the left by Q inverse, right? Q inverse undoes the Q there, and so we just get T alpha equals Q inverse of the right-hand side, T beta Q. That's what we're hoping for. Okay, and these are all matrices, right? This is a matrix, this is a matrix, that's a matrix. And so we actually have a special definition particularly about that. If A and B are n by n matrices over a field, we say B is similar to A if there exists an invertible matrix Q such that B equals Q inverse AQ. And incidentally, this is a symmetric relationship, because if that's true, you can multiply on the left by Q, right? Or you could even say multiply on the left by Q inverse inverse. And we're there. And then you could multiply on the right by Q inverse. And you have, well, A is similar to B. I mean, Q inverse is as good a matrix as any to be invertible. So this is a symmetric relationship. If A is related to B, similar to B, B is similar to A. This theorem then is saying that the matrix representation of linear transformation in any two bases are similar. Okay, so maybe an example is worth looking at. So let's sort of think about this example. Let T be a linear transformation, a linear operator on degree 1 polynomials defined by T of P equals P prime. That's the derivative function. So we all know the derivative function. Let alpha be the standard bases, let beta be the basis, x plus 1 comma x minus 1. And we'll use the theorem to find T beta. We need this fact. This will come up in chapter 3 of the textbook, how to find inverses, but we don't have it quite yet, so I'll just have the fact there. Okay, so what's the point? The big idea is that T alpha is easier to find than T beta, right? It's pretty easy to find what T alpha is. I mean, if you think about that, T alpha, if you're finding T alpha, I just have to know, hey, what does T do to the basis elements alpha? Oops, that should be an X, right? Well, the derivative of 1 is 0, the derivative of X is 1. And now I have to write them in the simplest possible basis. Gee, how many 1s is 0? How many X's is 0? 1, that's 1, 1, and 0 X's, right? So what's the matrix? 0, 0 is my first column, 1, 0 is my second column, right? Okay, so that's this representation. Now, from the theorem, you can sort of go back and forth between these. If these are similar, you sort of pick the most convenient Q. So we could pick a change of coordinate matrix, frankly, from alpha to beta or from beta to alpha. So I'll let you try this. My claim is it's actually easier to go from a more complicated basis to a simpler basis. So I'm going to pick Q to be the identity from beta to alpha because beta is the more simple, the more complicated basis. And hopefully you can see why this is. And you could pick Q to be the opposite, then your inverse is the opposite, and play the game the other way. Okay, so what's IV on the first basis element in beta? X plus 1. Well, I need to just know, since this is in terms of the simple basis, I just need to know how many 1s are there and how many x's. So 1, 1, IV of x minus 1. And it's just a bit more complicated to go the other way. How many x's? Sorry, how many constants? -1. How many x's? 1. So what is this matrix? This matrix is first column 1, 1, second column -1, 1. Okay, and then using the fact, what's Q inverse? Well, Q inverse is 1 over AD minus BC. That's 1 minus -1, so 1/2. That's called the determinant, by the way. And this, maybe I should have this, if it exists. Not all 2x2 matrices are invertible, but if they exist, this is what it's going to be. Okay, now on the diagonal, you swap the entries. So we take these two entries, we swap them. on the off diagonal, you just negate the entries. So that's 1 and that's -1. Okay, so that is Q inverse. Now, this theorem is really interchangeable, but we have to put the right piece in the right place. So if I have T beta, sorry, I have T alpha, I want T beta, the important thing is simply to get to the right place. So T alpha, right, because frankly, the alpha and beta in my example aren't necessarily the alpha and beta in here. I could let the thing labeled alpha here play the role of beta or vice versa. I just have to get to the right base matrix representation. So this is in terms of alpha. This goes from beta to alpha. So I'm going to put Q over here, okay? And then I'm going to put Q inverse over here. So just making sure this stays in beta the whole time. This goes from beta coordinates to alpha coordinates, processes in alpha coordinates, and then the inverse goes from alpha coordinates back to beta coordinates. Same as staying in beta all the time. Okay, so what's Q inverse? It's 1/2, 1, 1, -1, 1. What is T alpha? 0, 1, 0, 0. What's Q? 1, -1, 1, 1. Remember, matrix multiplication is associative, so it doesn't really matter which order. I'll multiply the first two. So row column 0, row column 0, row column 1, row column -1. One more time. Row column 1, row column 1, row column -1, row column -1. Okay, so what on earth is this thing? This is the matrix representation of T in terms of beta. So how could we check that? Let's try and sort of figure out what on earth we just did. So the matrix representation of T in terms of beta makes sense if we apply it to vectors that are represented in terms of beta. So let's just see what happens if I take the basis elements here, right? So what the first basis element does here is, so this is like, you should think of this as T. You should think of this as, this is T, that's that. But this is the matrix, 1/2, 1, 1, -1, -1. How do you represent that in terms of this ordered basis? Well, it's just 1 of the first and none of the second. So what's that multiplication do? That multiplication gives you 1/2 row column 1, -1. In other words, 1/2 -1/2. And so what should we be expecting to come out here? Well, remember, you're expecting to come out T of x plus 1 beta. But could we think about what that is? Well, what's T of x plus 1? That's the derivative, right? Well, the derivative of x plus 1 is really just 1. And then, so how do I express 1 in this funky basis? And this is telling me, well, 1/2 of the first basis element minus 1/2 of the second basis element will get you the derivative. And in fact, 1/2 x minus 1/2 x, those cancel. 1/2 of 1 plus 1/2 of 1 is 1. And so you can see it actually did what we intended.